This is chapter 27, example 3. What we need to do here is design a circuit that when a button is pressed, it divides an 8-bit unsigned binary number by 2 as many times as I need to do that to make that input less than 32. So the issue with this circuit is you're not allowed to use a comparator, which is not a big deal. It'd be very easy to use a comparator in this circuit, but we're not allowed to. Other issue in this circuit is it has an extra output that indicates when I'm done. Interesting problem. This is one of those problems where it's going to naturally, the only way I know how to divide by 2 is the shift register, so it's going to be shifting right, but I don't know how many times it's going to shift right, which is, the key to the problem. But notice that this is essentially analogous to a while loop in programming language. Essentially, I'm going to keep shifting while the value is 32 or greater. And so just for historical comment there. And so very first step in problems like this, or as in all problems, is to draw this high-level black box diagram. The output is, we'll get to that in a second. This is, we'll call it result. And we got a clock. Yes, we have a done signal. This done signal essentially tells when the output is ready. So since we're going to have to be doing some shifting here, while we're doing shifting, the output is technically not valid. We want to indicate to someone that the result is sitting there by asserting that done signal. So this circuit should be fairly obvious. The only way we know how to do division, particularly division by 2, is with a shift register. So that's going to be our starting point. I'm sorry, let's finish this up. We didn't get this value here. Now the issue with this value is I'm going to stop shifting when the result is less than 32. That means it's 31 or less. I can represent 31 with 5 bits, and so this the width of this output is going to be 5 bits by the time I'm done with it. Yeah, I just remembered that right here. So I think what we'll do is just keep it in the 8-bit world, and at some point we'll do this magic, getting rid of the 3 bits here and make it magic 5 bits, and we'll put a note on it. This is shift register. We gotta have a clock. We got a data input, and we can put a select in there. Got a select in there. We're going to use our standard shift register, universal shift register on this. This is the data coming in from the outside world, and this is 8. This is what we're going to be loading into this thing. Now the issue with the circuit is it's going to need a state machine, so we can partially fill that in. Certainly one of the outputs of the state machine is the done signal, and we need to control the shift register somehow, and that's going to be a 2-bit select output. And the select is a control input for the shift register. It's naturally an output from finite state machine. State machine needs a clock. The issue here, how are we going to make sure it's less than 32? So the issue is when we have an 8-bit number, if those top 3 bits are all 0, then that number is less than 32. Now we could drop a comparator in here, but the problem said not to. So what we're going to check for is to see if those top 3 bits are all 0. And we'll pull these 3 bits off. And what this is going to be is saying, we'll call this LT32. And we'll put a note here. All those 3 MSBs are 0. So the top, the next one, and the end gate here, they're all 0. Then I know that value is less than 32. And this becomes my status input. Like I said, I could use the comparator, but we opted not to. And so this is going to be LT32. For now, that looks pretty good. If I made a mistake, forgot something, I'll come back and fix it. So this is a typical circuit that you see a lot. Essentially, it's waiting for a button press. So long as the button doesn't get pressed, it goes back to the wait state. Without really thinking about it, pretty much is going to be a divide state. So when that button gets pressed, I'm going to start dividing. And I'm going to keep dividing. We're just going to wing this. I'm going to keep dividing until something happens, and then I'm going to keep dividing until LT32 is asserted. And so that looks pretty good as is. Let's go ahead and fill these in. This is a shift register. The first thing we need to do with the shift register is to load it. I can make that load signal, which is going to be the select signal. I can make that as a Mealy machine. And speaking of which, let's go ahead and fill this in. We'll call it hold load shift left. Okay, I have to put this in here. If I didn't put that in there, we'd not really know how the shift register works. So this is somewhat arbitrary. We're going to follow it. While I'm waiting here, I'm going to make sure, because that output is persistent, it requests that the output be persistent, so I certainly need to be holding that. But someone presses a button, I can load this thing. Now that means by the time I get into this divide state, I have loaded that input value already. Okay, so in this state, I'm going to stay here in this state so long as LT32 is not asserted. So once it gets asserted, I go back to the beginning state, back to the wait state, and essentially I'm going to be holding that output as directed by the select signal. At this point, I need to do stuff based on the status signal. LT32 is a status signal. So if, in this state, if LT32 is not asserted, I need more space here. I need to shift it right. Okay, otherwise, if it is less than 32, I'm done, and I need to hold it. I'm trying to think of what else I need to do here. I need to handle the done. So essentially in this state, it says I'm done. Whenever I'm in this state, I might actually be done, but chances are I'm not done. It needs to do some division, so I'm turning the done off in that state. Let's see how this is controlled. I see a state machine, so it's circuit controlled. The button goes into, oh, that's right, okay, I almost forgot that. Button goes into the state machine, which we can call that circuit controlled. I think that's all I can think of in this problem. Take one last look, see if I forgot anything. Select and done I've handled in both states. Let's call it done.